All right, we're continuing on in section 5.6 when we're looking at applications and models of exponential growth and exponential decay. Here we're actually going to work through one of your homework problems that you have. Here we have radioactive element carbon-14 has a half-life of 5,750 years. Scientists determined that the bones from Mastodon lost 73.7 of the carbon-14. How old were the bones at the time that they were discovered? One thing I wanted to show you guys is there are actually videos that you can click specific to all of these that you can watch. You don't actually have to wait around to watch a video from me from all of these. And some of them are better than others. This one here.
This application involves carbon dating. The radioactive element, carbon-14, has a half-life of 5,750 years. The percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3%
Now, these videos are available to most of the homework problems that you have, and you just click on them and they'll come right up.
We will use
this is the model that we were looking at
exponential
earlier.
decay model. P of t equals P sub 0 times e to the negative kt power for k.
And I'm just going to stop right here. One thing that's important to know that these videos are going to give you, they're going to say, well, k is always going to be positive. Just remember that if k is positive, then you have exponential growth. Here they have the negative sign built into the equation. And what that means is you're going to have decay overall. I tend to try not to confuse these two. Just remember that if you have negative stuff here, you're going to get that exponential decay model, which is what this problem is actually talking about. But there's using k is going to be positive here. So it's a little bit confusing. But just understand that if it's a negative overall over here, even though your k is positive, then you're going to have exponential decay.
K is greater than 0. We first want to find k.
So
equal the ln of 2 over the half-life. The half-life is given in the problem of 5,750 years. Calculating, we see this is approximately 0.00012.
I will say it's very important here that you carry out as many decimal places as you can use. She wrote down 5 here. I would suggest going like 6 or 7 in this case to get a more accurate answer. But yes, when you're finding half-life, and this comes from the doubling formula that we had earlier, you eventually end up with this. So if you know that the amount of years it takes to get half of where it's supposed to be, you can calculate that fairly quickly using this k is equal to the natural log of 2 over t.
Let's substitute that value for k in our model. So we have P of t equals P sub 0 times e to the negative 0.00012 t. Now we know that the wrappings have lost 22.3% of the carbon-14, which means that 77.7% of the carbon remains. So we can express P of t, we can substitute for P of t, 77.7% of the original amount, P sub 0. So that equals the original amount times e to the negative 0.00012 t. Let's convert this percent to a decimal, and we have 0.777 times P sub 0 equals P sub 0 times e to the negative 0.00012 times t. Next, we will divide on both sides by P sub 0.
So she's dividing both sides by P sub 0. When we did the doubling formula earlier, I had 2 on the left and 1 on the right. You actually don't need the p sub 0 here. She's just putting that in as a placeholder to understand that we lost. We have 77.7% remaining of what we initially had.
Then we have 0.777 equals e to the negative 0.00012 t power. Now let's take the natural logarithm on both sides. We have the ln of 0.777 equals the ln of e to the negative 0.00012 t. We know the ln of e to the x is x. So we can rewrite the expression on the right as negative 0.00012 t. Solving for t, we'll divide on both sides by negative 0.00012. And we have t equals the ln of 0.777 divided by negative 0.00012. And then using our calculator, we evaluate and we have t is approximately 2,103, which tells us that the linen wrappings were about 2,103 years old.
Okay, so that's a very good example of where you can use video to solve these problems when video is available. And also, she did actually a really good job showing all the steps you need to do to solve this problem.